Welcome to G Fun Facts Online. Today, we are stripping away the hype and diving straight into one of the most significant events in modern physics that occurred just recently. On the night of February 14, 2026, while the world was celebrating Valentine's Day, a team of scientists deep beneath the snow-covered pine forests of Dubna, Russia, achieved something that has been 19 years in the making. At exactly 23:42 Moscow time, inside the control room of the NICA complex, applause erupted. It wasn't for a romance, but for a resurrection. For the first time in history, two counter-propagating beams of heavy xenon ions were stably circulating within the rings of the NICA collider. This isn't just another science news headline. This is the activation of a time machine. The NICA facility, which stands for Nuclotron-based Ion Collider facility, has officially unlocked the door to what physicists call the Little Bang. By achieving this stable dual circulation, humanity is now poised to smash atomic nuclei together at velocities approaching the speed of light, effectively winding the cosmic clock back 13.8 billion years. Today, we are going to break down exactly how this machine works, why this specific type of collision is different from anything happening at CERN, and how this massive engineering project will revolutionize everything from cancer therapy to Mars exploration. Let's start with the engineering feat itself, because to understand the magnitude of this breakthrough, you have to understand the sheer complexity of the machine. NICA is not a single device. It is a sprawling vascular system for high-energy particles. The success on February 14th was the result of a technological marathon that began a year prior, testing cryogenics, vacuum chambers, and superconducting magnets. But the ultimate test is always circulation mode. In particle physics, keeping a single beam of particles moving in a circle is incredibly difficult. It is often compared to balancing a pencil on its tip while riding a unicycle. You have these positively charged particles that naturally want to repel each other and fly apart. They have to be constrained by powerful magnetic fields and focused into a hair-thin strand. Now at NICA, they are doing this with heavy ions like xenon. Xenon ions are massive and cumbersome compared to the protons used at the Large Hadron Collider. To keep them stable is hard enough. To keep two beams of them stable simultaneously, moving in opposite directions within the same magnetic structure, is a feat of high-wire acrobatics. On that night, the injection sequence began at the booster, a smaller synchrotron ring that acts as the on-ramp. The ions were stripped of electrons, accelerated to relativistic speeds, and injected into the nuclotron, the heart of the facility. From there, they were kicked into the main collider rings. Dr. Anatoly Sidorin, the deputy head of the accelerator department, noted that usually the beam degrades quickly due to imperfections. But on this night, it held. They injected the counterbeam, and it held too. This state is called collision readiness. It means the collider's optics are perfectly aligned, and its magnetic muscles are strong enough to hold the densest matter in the universe in a tight grip. But why build such a colossal machine? What are we looking for? This brings us to the science of the Quark-Gluon Plasma, or QGP. In the standard model of cosmology, the universe began with the Big Bang. In those first few microseconds, the universe was too hot for protons and neutrons to exist. Instead, the fundamental building blocks of matter, quarks and gluons, roamed free in a super-hot, super-dense soup. As the universe expanded and cooled, a phase transition occurred. The quarks were confined into protons and neutrons, locking away that free state of matter forever. We live in this frozen universe today. We have never seen a free quark. They are always bound inside atomic nuclei. NICA is designed to melt that ice. Now, you might be thinking, hasn't the Large Hadron Collider already done this? Yes, but NICA is doing something different. The LHC operates at incredibly high energies, creating a plasma that is very hot, but not necessarily very dense in terms of net baryon density. That is, the number of protons and neutrons packed into a volume. NICA occupies a unique niche. It operates at a lower energy range, between 4 and 11 GeV. This seems counterintuitive. Usually, we think higher energy is better. But in this case, by colliding ions at these specific energies, NICA doesn't just burn the nuclei away, it compresses them to maximum density. Theoretical physicist Dr. Elena Petrova uses a brilliant analogy here. Think of boiling water. The LHC turns water into super-hot steam instantly. NICA is exploring the point where water is under such extreme pressure that it is neither liquid nor gas, the critical point. They are looking for the maximum density of baryonic matter, the same density found in the crushed cores of neutron stars. This search for the critical point on the phase diagram of nuclear matter is the holy grail of modern high-energy physics. Finding it would confirm our theories about how the universe evolved and how mass itself emerges from the interaction of particles. To achieve this, the facility uses some mind-bending technology. One of the most critical components is stochastic cooling. This is effectively Maxwell's demon brought to life. An ion beam is like a swarm of bees. They buzz around, creating disorder or heat in the beam. NICA uses sensors to pick up the air in position of a slice of the beam. This signal is sent across the ring via a shortcut cable, which is faster than the ions moving in the curve. A kicker electrode receives the signal just as the ions arrive and gives them a nudge to correct their path. NICA performs this correction millions of times per second, reducing the entropy of the beam to pack ions tighter than natural laws would usually allow. This is what allows NICA to reach the luminosity required to see rare events in the plasma. Furthermore, the cryogenics involved are staggering. To make the magnets superconducting, they must be cooled to near absolute zero. On February 14th, the magnets were held at 4.5 Kelvin, or minus 268.65 degrees Celsius. Chief engineer Viktor Ivanov pointed out that they are creating the hottest point in the universe, the collision, inside a ring that is the coldest place in the universe. The temperature gradient from the collision point, which is trillions of degrees, to the magnet coil, which is near absolute zero, is the steepest in nature. It requires insulation technology that borders on science fiction. However, NICA isn't just about the early universe. It has a massive applied science program called ARIADNA. This program turns the collider's beams into tools for medicine and space exploration. First, let's look at cancer therapy. Heavy ion beams have a unique property called the Bragg peak. Unlike X-rays, which deposit energy all the way through the body, damaging healthy tissue, heavy ions deposit almost all their energy at a specific depth and then stop. This allows doctors to target deep-seated tumors with millimeter precision. NICA is researching flash therapy, a technique where the entire radiation dose is delivered in a fraction of a second, killing cancer cells while inexplicably sparing healthy tissue. Then there is the Mars Mission Simulator. Space is filled with galactic cosmic rays, heavy ions moving at relativistic speeds. These are the single biggest danger to astronauts traveling to Mars because they can destroy DNA and fry microchips. NICA is one of the few places on Earth that can simulate this radiation. They have stations exposing cell cultures and microchips to these beams. If a microchip can survive NICA, it can survive the trip to Jupiter. Additionally, there is research into transmuting nuclear waste. By firing a high-energy beam into a subcritical nuclear reactor, scientists can burn long-lived nuclear waste, turning isotopes that stay radioactive for 10,000 years into isotopes that are safe in just a few hundred. So what happens next? The breakthrough on February 14th was the dress rehearsal. The main event is scheduled for the summer of 2026. In August and September, the NICA team plans to bring the beams into collision for the first time inside the MPD, or multi-purpose detector. This detector weighs over 1,000 tons and is designed to track the thousands of particles produced in a single gold-on-gold collision. When those collisions happen, sensors will light up and computers will crunch petabytes of data, looking for the telltale flow patterns that indicate the presence of the Quark-Gluon Plasma. We are about to look into a mirror that reflects the universe as it was 13.8 billion years ago. We are about to learn why we have mass, why protons don't fall apart, and what lies in the crushed hearts of neutron stars. The Big Bang is no longer just a theory to be calculated. At NICA, it is about to become an experiment to be observed. The machine is alive, the beams are dancing, and the little bang is imminent.